We now know the technique of drain feedback biasing, but our aim is to realize a common source amplifier with a smaller gain sensitivity. So what we have to do is to marry the drain feedback bias with the small signal picture of the common source amplifier and come up with a circuit which behaves like a common source amplifier in the incremental small signal picture, but whose biasing is based on drain feedback. Okay. Now, drain feedback bias has this arrangement. The desired drain current I0 is connected that way, and the drain voltage is fed back to the gate. Let me call this MOS transistor M1, and this is VDD, which really means that the supply voltage VDD is connected between this upper rail and ground. Okay, so it's quite common to show sometimes just a line that is marked VDD. It means that there is a battery of value VDD between this point and ground. Now, what is the common source amplifier? Common source amplifier is one where I have a signal source and I have my transistor, gate, drain and source, and this is the control source inside the transistor, GM VGS, where VGS is the gate source voltage. The source is grounded and the load is connected between drain and ground. This is the essence of the common source amplifier. Now, of course, we could have extra components. First of all, we could have capacitors which are useful for adding some value of bias to the signal, assuming that the signal is above a certain frequency. Okay. Also, we may have other resistors useful for biasing. If you recall the old circuit, we had R1 parallel R2 over here, and then we had the drain bias resistor RD over there. Okay, these may or may not be there. That depends on the exact biasing arrangement. Okay, but the stuff that I have shown in black, that is the common source amplifier. So somehow we have to make sure that this signal Vs, or most of it, appears across gate source, okay, and then we have a load resistance RL, and this RL must appear across drain source. Okay. Now, of course, this must happen without disturbing the bias. Okay. So, let us try to do this. We already know all the principles we need for this. Okay. We know how to add signal to bias. As usual, we will assume that the signal is at a frequency greater than or equal to some omega naught. Okay. So, we don't have DC signals. Okay. So, in this case, we can use AC coupling techniques. We can use a capacitor to couple the signal, and we know how to calculate the value of the capacitor. Okay. So, given this, we can proceed with trying to turn this into a common source amplifier. Okay. So, let us do that. As usual, I would encourage you to think through the steps yourselves, okay, to find out exactly how to do it, and it's fun. This is how you invent circuits. This circuit we are going to come up with is already well known, but later when you become more experienced, you can come up with new circuits, and that is why a chain of logical reasoning just as this one. Okay. So, you know certain building blocks, and you put together those building blocks to make more complex circuits. Okay. So, we have the biasing picture or setting up of the operating point. And in that, I will continue to show it like this. Please understand that there is a battery between this point and ground. This is M1. Okay. So the essential feature here is that drain is connected to the gate for biasing, and the signal picture I will show a MOS transistor instead of its small signal picture. I could also show that. Let me show both, and later, depending on convenience, I will show only one or the other. Okay. This is the small signal picture. What should happen? The source should be grounded in the small signal picture, and the source Vs must appear here. This is the gate, this is the drain, this is the source, and RL must appear over there. Okay. And of course, the transistor has to remain in saturation, but that is guaranteed by this biasing arrangement, because in this case VDS equals VGS. Okay. And it's definitely more than VGS minus VT as long as the threshold voltage VT is positive. Okay. Or if I draw it with the MOS symbol, I have Vs and Rs appearing across the gate source and RL appearing over here. This is in the small signal incremental picture. Okay. Now first let's try connecting the load resistor. Okay. The load resistor must appear between drain and ground, or it must be connected to the drain. Okay. So let me take the load resistor RL, which could be grounded. This was explained earlier while discussing the original common source amplifier. RL is a representation of whatever follows. Okay. It may not be a physical resistor. Okay. So one side of it is grounded. Now what do? It has to get connected to the drain. So the first naive attempt is to simply connect it to the drain like that. Now please think about what problems this could have. One problem that is immediately evident is that we wanted this current I0 to flow through the drain of the transistor. Okay, the drain current has to be equal to I0. But in this case, what happens? I have a certain value of operating point drain source voltage VDS, and that appears across RL. So VDS by RL will flow that way. Okay. So the current, in steady state, this drain current will not be equal to I0, but it will be equal to I0 minus VDS by RL. Okay. So this is an unnecessary complication. Okay. You don't want this RL to draw any operating point current. It's totally useless. There is no point in doing that. So what do we have to do? We have to connect it differently. We can't connect it directly. So somehow only for signals it should appear across this, and that is easy if the signal is above a certain frequency omega naught. Okay. So this is known as AC coupling, and the way we connect RL to the transistor is exactly the same as our original common source amplifier. We connect it through a capacitor. Okay. So that if the capacitance is very large, then all of the signal voltage VDS will appear across RL, but the DC here is blocked. Okay. So sometimes this is also known as DC blocking capacitor. Okay. The operating point here will be VGS, whatever the VGS is. It is given by VT plus square root of 2 I0 by Kn, as we have evaluated earlier. The operating point voltage here is 0, and the difference will be dropped across the capacitor. Okay. So let me call this C2 following my original notation. Now what should I do about the gate? The gate voltage must get connected to the drain for DC biasing, but it should get connected to this source combination of Vs and Rs for signal, for AC. Okay. For DC it should go to the drain, and for AC it must go to VSRS, basically the signal source. How do we arrange this? This is again something that we know. Okay, we know how to add a certain DC to a certain AC signal source. Okay, That is, we want a terminal to be connected to terminal A for DC and terminal B for AC. We know how to do that. This is exactly what we did earlier also, right? In case of the common source amplifier, if you recall, the gate, I won't show the complete picture on the drain side, but the gate we had to get VDC plus Vs. So what did we do? We have the signal source Vs and we have the DC source VGS 0, whatever the quiescent value, the operating point value of VGS is. Okay. How did we do this? So we connected VGS 0 through some resistor and the signal source through a capacitor. Okay. Now, of course, we have to satisfy some more conditions. This Rx has to be much more than Rs, so that all of Vs appears here, and this C1 has to be much more than 1 by omega naught Rs plus Rx and so on. Okay, so this was the essential idea. Now, of course, in the common source amplifier, we didn't have a separate source VGS 0. This itself was derived from a voltage divider powered by the supply voltage VDD. Okay, but now the idea is exactly the same. The gate has to get connected to something for AC and something else for DC. So what we do is the following. Let me show this broken here. This point should get connected to the drain for DC. Okay, so I connect it through a resistor. Let me just call it RG. At the same time, it should also get connected to the signal source for AC. Okay, so I connect it to the signal source through a capacitor C1. Okay, and now we have to make sure that this C1 is much larger than something, and we have this RG. We have to find out the effect of that and so on. Okay, so what we have done is to use the principle of AC coupling to connect the signal source to the gate source and the load RL to the drain source. Okay, so I hope the logic is very clear. If not, please replay the lecture and follow the logic once more. It's very important that you understand the logic behind every step of this. Okay, so the common source amplifier using drain feedback. I will show the complete picture here. Okay, so we have a current source I naught. The feedback to the gate is provided through RG, and that's okay because no DC flows into the gate, so there will be no DC voltage drop across RG. Okay, earlier when we were coming up with the biasing arrangement, we had connected the drain directly to the gate. Now we connect it through RG, but it makes no difference at all because no DC flows through the gate. Okay, and the signal source is connected to the gate source via C1. The load resistance RL is connected to the drain source via C2. Okay, so this is the topology. Like I said, hopefully you understand all the logical steps leading to this. Now we have to, of course, go and analyze this, use our circuit analysis skills and analyze the effect of everything. So we need to determine the constraints on C1 and C2 just like before. Okay, also we have to analyze the effect of RG. Okay, because RG is not a component that is in the basic common source amplifier. Okay, so if you look at this is the basic common source amplifier. It has the transistor, signal source and load, that's all. The RG is something extra. It is similar to the bias resistors we have in the original common source amplifier topology. We had R1 and R2 on the gate side and drain bias resistor RD, and we analyzed the effect of that and saw what happens. So similarly we have to do it here. We have to find the effect of RG and see what is a good value so that it doesn't significantly or adversely affect the common source amplifier. Okay.